All right, so we're now live on YouTube. Everybody can see the slides? Yes?
Yes.
Okay, cool. Thank you. All right, so we made a small change over our schedule because we know that quiz number 5 is coming up next week. So instead of covering all the materials for graphs, which is going to be on the final, we decided to use this week as a review week. So today, my recitation's most problems is actually surrounding combinatorics. There's a few problems surrounding probabilities. And then in this week's discussion session, which is on Thursday, we are also going to cover more problems over probabilities as well. And today's problem, majority of them should be fairly easy. And it's designed to test some of the fundamental knowledge you have for combinatorics and probability. And most of the problem you should be able to solve within a minute. Some of them probably half a minute. Okay, so there's a large number of problems today, and I'm hoping to cover all of them. All right, so a few announcements that quiz number 4's grades has been posted. A reminder, you have a week to file a regrade request through Gradescope. And then the TA has also shared the distribution of the grades for quiz 4. Overall, it's a quiz 4 material. It's easier than the previous 2 quizzes. So, and people, majority of the students have done quite well for quiz number 4. So last week's discussion sessions, we have covered some of those quiz 4 problems, and then some of those answers will be posted over Piazza. But if you have a specific question regarding the solution for the quiz, please feel free to post them over Piazza, and then the TA will be able to share the solution with you. And then most importantly, the last quiz, quiz number 5, is going to be this next Tuesday on November 24th, and it's going to be a 1-hour window between 7:30 and 5 p.m. We have extended the window to have 1 more hour so that students have more flexibility. But keep in mind that the exam is still just 1 hour, and with a 30 minutes grace period for submission only. So we're going to have review for the combinatorics and probability today, Thursday, and also on Monday, TA Zoe and TA James, they are going to have extra review session for quiz number 5. And then it's going to be recorded and available on YouTube as well. Okay, so the TA has started grading homework 5. And then hopefully the grading will be done by this Friday as well. And remember also we have, I believe, another homework due that is also due this Friday. Okay, so again, this is a distribution of quiz 4 grade. As you can see, majority of the students, more than 75% of students has got a grade above 90 or so. Okay. All right, so as I mentioned before, we're going to go through some fundamental questions. This recitation, they are not very difficult, so you should be able to solve this really quickly. And I really, really highly encourage you to participate in the discussion, or if you know the answer, feel free to raise your hand using Zoom, the raising hand, or you can type in your solution and Zoe will read your solution as well. So the first question is on combinatorics. It's basically surrounding multiplication principle. Again, this should be takes you roughly 20 seconds. So the question is, there's 4 appetizer choice, 5 entry choice, and 3 dessert choice. How many total choice are there for a particular guest? Anyone?
Jackson, go ahead.
Jackson, remember to unmute yourself. Zoe, can you hear Jackson? I can't.
I cannot either.
Okay, Jackson, if you have the solution, do you mind typing it? We cannot hear you.
Hello?
Yes, go ahead.
Can you hear me now?
Yes.
Oh, looks like you're muted again.
60?
Okay, how do you arrive at 60?
I did 4 times 5 times 3.
Great.
4 times 5 is 20, 3 times 3 is 60.
Yes. So to use the multiplication principle, right, you have sort of 3 steps for the solution, and each step has a number of choices. You have, the first step, choose your appetizer. Second step, choose your entry. Third step, choose your dessert. So that's 4 times 5 times 3. Okay. So thank you. So that's correct. Let's look at the next one. How many 3-digit number are divisible by 7? Okay. Anyone have a rough idea how you would like to solve this problem? And this should again be something solved within between 1 minute to 2 minutes. Feel free to raise your hand using Zoom, or you can type in your solution or type in your idea of the solution. Any volunteer? As you are thinking about the solution, let's give you a small reminder. It has to be 3-digit number. So it has to start with 100 and 101 and so on. And the last number you're going to consider is 999. Okay. And then you need to look at them to see which one is divisible by 7.
In the chat, Brendan said 128.
128. Great. How did you arrive at the solution? You can either unmute yourself or you can type.
Let's see, he did 999 divided by 7 minus 99 divided by 7.
Okay, so the way, yes, this is one really good solution. So what this first number is sort of number of, so this is number of integers that is divisible by 7 that has at most 3 digits. Okay, but it's include, 1 digit, 2 digits as well. And then it's kind of subtract the number of integer that is divisible by 7 with at most 2 digits. Okay, so you're using sort of exclusion principle. So that's version number 1. That's a good solution. But you have to be a little bit careful. When you divide by 7, you want to make sure that either you're taking the floor or the ceiling. In this case, you want to take the floor. And then you want to validate it on the side as well to see this is the right solution. The second version of a solution is that I can sort of enumerate what are the integers between 100 to 999, which is, for example, the first number 105 is the first number that is divisible by 7. So it's 7 times 15. And the next number divisible by 7 is you add 7 is 112, which is 7 times 16. And you keep going until the last number before 999 that is divisible by 7, that's 994, which is equal to 7 times 100, 142. So now you basically are counting, how many numbers are there? There's 15 copies of 7, 16 copy of 7, 17 copies until 142 copies. So you have 142 minus 15 plus 1. That is also 128. Okay, so that's a second way to solve this problem, but they both give rise to the same answer. Okay, any questions? If there's no more questions, so let's move on to the next one. Okay, so now if we move into further counting, we have 2 types of formula, permutation and combinations, right? So permutation formula, we used to use P, n k is n factorial over n minus k factorial. And when you think about permutation, what you have in mind is essentially the slogan that the order matters. Okay, that's when you use the permutation. If you're using combination, is of course the situation where the order doesn't matter. In fact, if you look at the formula, it has this extra term right here, which is really P of nk divided by k factorial. This is really kind of get rid of the overcounting by permutation. So again, in this case, order does not matter. That's why it's a number of permutation divided by all the instances of the permutation. So it's get rid of the order in there, okay? So in most questions you're going to see surrounding those type of problem is try to figure out which formula to use, okay? So let's start with the first one. Right, so again, this should take you roughly half a minute, right? So, you have 10 kids getting into a line to buy ice cream. And how many ways are there to form a line? Okay, do I have a volunteer?
I'm not seeing a volunteer, but there is a question about the quiz.
Yeah.
Can we just write like the permutation, like PNK or CNK with N and K being variables or numbers?
So if you have taken, I think it would be good to read the instruction from the practice quiz number 5. The instruction goes that if it's a very complicated number, for example, C99 over 5, right? Then you can just specify the actual formula itself without actually come up with the actual integer. But if it's a very simple formula, like say 6 times 5 times 4, then we do expect you to provide the actual integer itself. So that is a guideline. So for example, here, I would only ask you for the actual, just the formula itself without giving me the integer.
Let's see. Okay, couple more. So there are Jackson and Kevin both got 10 for the problem, and then there's another question on the quiz.
Okay.
If our final answer is,
yeah, go ahead.
If our final answer is correct, but if we write the permutation formula wrong, would we lose marks there?
So if first of all, your formula has to be consistent with your final integer number if you decide to do the integer number, right? But like I said, if it's a complicated computation, the formula itself would be all right, but you need to make sure your formula is correct. So if your formula is incorrect, but your actual integer is correct, you will lose points from it, because the best way for us to understand how you arrive at your solution is you need to provide proper justification how you get to that solution. So yeah, so make sure your formula is correct. Okay, so you said some 2 students has posted the answer. What is the answer?
10.
Okay.
Factorial. 10 factorial.
10 factorial. Exactly. So this should not be a hard question. If you have 10 kids getting a line, you think about you have 10 locations that they're going to get in line. The first location, there's 10 choice. One of them can be the first person. Then the second one has 9 choices, 9, among the rest of the 9 kids, and so on and so forth. And you multiply them together. And at the very end, the last location, you have 1 choice remain. So that is 10 factorial, right? But also, this is 10, 10. All right. Okay, so this should be easy. Let's move on to the next one. Okay, so we want to select a subset of 5 people from a set of 18 junior students and a subset of 7 from the set of 16 senior students to form a committee. How many ways are there to form such a committee? So again, a hint, this we're going to use multiplicative principle as well. Because you have 2 steps, right? The first step, you're selecting 5 people from 18 junior student. The second, you're selecting 7 from the 16. And one thing to keep in mind, does the order matter in this case? I see some people shaking head. So the order does not matter, okay? So if order does not matter, then the hint is you're going to use the C formula, not the permutation formula. Okay, so do I have a volunteer?
Yeah, a couple people in the chat said combination of 18 choose 5 and 6 choose 7.
Okay, so choose 5 out of 18. That's how many ways I can choose 5 people from the junior students times how many people I choose from 16 from the senior students. And it's multiplication again, because I have a 2-step process. I'm multiplying the possibilities for every step, and that's it. Okay. So again, if this is exam, this will be the good enough solution. I would not ask you to expand the formula further. Okay. Any questions so far? Okay. So feel free to ask me to slow down a bit, because at the beginning, my recitations, we have questions that are fairly easy to do. So that's why I'm going in a relatively fast pace. But feel free to ask questions and ask me to slow down. Okay. So now next question, again, is combination, counting problem. How many license plates, we're going to just use numbers right now, consists of 6 digits with exactly 2 of the same digits appear in this license plate. Okay, so again, you have essentially 6 locations where each location you have 10 choices of numbers, but we want you to count those license plates with exactly 2 of the same digits. Okay, so again, think about this problem from multiply principle, and I could give you a hint that there are 3 steps to form those license plates. Okay, and for this problem, you have roughly a minute. And feel free to type in if you have thought about how to solve this problem. So if you recall from our lecture, which has been a while ago, our lecture, we also have a similar problem, but slightly different, where we're asking how many of those permutations are there if I want to enforce, digits of the same number to be adjacent to each other. So you can think about that problem as additional take-home one. So.
All right, there are a couple answers in the chat right now. Do you want me to go ahead with them?
Yes.
So let's see. First one is 10 times 6 choose 2 times permutation of 9 and 4. And then another solution is 10 times 9 choose 6. And then the last solution is 9 choose 1 times 1 choose 1. This one is kind of long. Times 8 choose 1 times 7 choose 1 times 6 choose 1 times 5 choose 1. And it looks like there is one more solution.
Okay.
9 choose 2 times 7 choose 1 times 6 choose 1 times 5 choose 1 times 4 choose 1.
Okay. So let's look at all these possible solutions. Okay. And what I'm going to do is I'm going to say, how do I solve this? I mean, of course, not all those solutions are equivalent. So only one of them, or maybe a few of them, are equal with the same solution, but let's look at this 3-step process. Okay. So the first process is I'm going to, among the 6 location, I'm going to choose 2 location. Remember, it's 6 digits. And then 2 of those digits has to be the same. So that means I'm going to choose 2 of those 6 locations to repeat a particular digits. So the first step is to choose 2 out of 6 locations for the same digits. Okay, so you have 6 locations, you choose 2 of them. It's C of 6, choose 2. Okay, now the second step is I need to choose a digits to repeat itself, right? There's total of 10 digits. So we want to choose 1 digit to repeat. And because there's 10 different digits, my choice is 10. Okay, or is equal to C of 10, choose 1. All right. And the third step is once I choose a digits to repeat, and once I choose a location to repeat the digits, remember the remaining of the locations has to have unique digits. And it's going to choose among the remaining 9 of them. So fill the remaining 4 locations with unique digits. Because I already choose 1, I have a total of 9 choices. And in this case, the license plate, the order does matter. So it's P of 9, 4. So the total answer is actually the first solution we see is 10, which is step 2, 6 choose 2, step 1, and permutation of 9, 4. All right. So now the question is what happened to the second solution? What was the issue? So, or is there any issue? So again, the first part is correct. You're going to choose digits that you're going to repeat yourself. But then there may be a little bit overcounting of 9, choose among 9 digits, you choose 6. So I don't think this gives the same answer specifically because it was not pay attention to the detailed step process. So the next one, let's see, we have to judge whether this gives the right answer. Can anyone who poses answer C or answer D explain what is the logic behind it?
Okay, there are a couple, let's see. Okay, there's a few different things to read off. So okay. There is a question, is 10 times 10 times 9 times 8 times 7 times 6 a possible correct answer?
Well, if I were going to split it, right? Okay, so let's add one more page. Well, so again, I want you to pay very special attention. When you solve a counting problem, it's not just say, okay, I will give you a formula, but rather what I would like to see in the actual exam is a logic behind this counting. Okay, so the correct solution, as I mentioned before, is 10 times C times 6, 2 times P of 9, 4. Okay, if I were going to expand it, what is this? This is 10 times 6 over 2 is 6 factorial over 4 factorial over 2 factorial, right? And then this is 9 factorial over 5 factorial. All right. So if I were going to expand it, this is 10 times 6 times 5, 2 times 1 times 9 times 8 times 7 times 6. Okay, which is 10 times 15, which is 3 times 5 times 9 plus 8 times 7 times 6. And then the question was, what is the solution with the question?
Oh, it was really close. It was 10 times 10 times 9 times 8 times 7 times 6.
Yeah, so the quick answer is this one here is not correct, but the rest is. right? So what is happening is that we have this permutation term and we have this combinatorial term. All right. Okay, so it's very important again.
The next question.
Oh yeah, sorry, let me finish this. It's very important when you actually try to solve a combinatorial problem to explain how you come up with that solution, right? For example, if you say my solution is this, what is logic behind every step? That assuming that you are looking at a number of locations and then counting how many choices are there to fill that location. But you have to be very clear how you arrive at this solution. Okay, so in order to receive, for example, partial credit. Okay, next question.
Next question is, why is 9 to the 4th wrong instead of a permutation of 9 and 4?
Because, okay, so yes, so that is a common mistake for this type of problem. If I do 9 to the 4th, what you are doing is to say that I have 4 locations and each of the location has 9 choices. Okay, that's how you arrive theoretically on 9 to the power 4th. However, remember the problem is only exactly 2 of the same digits. So if you do 9 to the power 4th, you are allowing most possibilities of repeating digits. That is not allowed. That's why you should not be counting 9 to the power 4th. Because the way we are dividing this problem into 3 steps is to first make sure there's only 2 digits that are repeating themselves, and then the rest cannot repeat themselves. But if you're doing 9 to the power 4th, you're allowing potentially, for example, a particular counting in this 1111 is a particular configuration, which is overcounting.
I guess I read it as exactly 2 of the same digit, meaning no more than 2 of the same digit, meaning you could have repetitions of other digits as long as it's not the same digit.
Okay, so that's not the intention of this problem, but we will try to make it clear in the problem. So the way this is interpreted, exactly 2 of the same. So okay, so the way you are thinking it is make it slightly more complicated even, but the intention of this problem is to say you only have 2 digits out of the 6 digits that is the same, and then the rest has to be different. That's how this problem should be. Yeah, but this is a good question. And hopefully when we are creating for our exam, we will be very clear what we mean by this, right? Yeah, but your version of the problem is making it a little bit more complicated. So, okay, so yeah, so I was saying that there's maybe variation of this type of problem. For example, how many what is the number of license plates do you have? If exactly, say 2 of the same digits are adjacent to each other. So what does this mean? That means, for example, 65543 is allowed, but 65453 is not allowed because I want to enforce adjacency. And if you have seen the homework problem, some of the homework problems have a similar flavor, which is I have a bunch of, boys and girls sitting in a circle, and, the 2 girls have to be adjacent to each other, or I have to say boy and girls cannot be sit next to each other. Like there's many different variations of it that changes how you solve this kind of counting problem. Okay. All right.
There's a couple more questions.
Sure.
So there's one about the homework. Should we explain the process in the homework or the quiz?
Yes, you should. So for you to gain partial credit, you should always explain why you arrive at that solution. Okay.
All right. And then the second question is 10 times 6 choose 2 times permutation of 9, 4 not identical to 6 choose 2 times permutation of 10, 5, wherein 10 numbers we can only choose 5 because 2 of them have to be the same digit?
Okay, that's a very long question. Sorry, just a second. I might have to read it. Okay, so
yeah, I put it in the calculator and it looks like they do come out to the same amount. So I think that should work.
Yes. So again, right, if the final answer is the same, this means that you need to just provide a justification. Remember, there's multiple ways of arriving at the solution. As long as your solution is correct and you can justify how you arrive at that solution, it should be fine. Yeah. Okay. All right, so let's move on to the next one. We haven't really gotten into the more complicated solution yet, and we have 20 minutes left. So how many possible sequence of 10 coin flips give exactly 3 or exactly 4 heads? Again, this is again a counting problem, and this is where you are going to use the addition, the rule of addition. Okay, anyone has, so for example, you know, head, 3 head, and then remaining is tail. This is one allowable configuration, for example, right? And so on. So there's multiple different solutions, possible solutions. So what is a formula? Again, I'm not asking for the integer solution. I'm just asking for the actual formula itself.
And let's see, Brandon said 10 choose 3 plus 10 choose 4.
Exactly. So why this is using addition is because in this particular case, you have 2 different type of configuration and they are mutually exclusive. So you can just add them together. But later on, when you can have problems that is not mutually exclusive, then you have to subtract the cases that is duplicated. All right.
All right, and then there's a question, why are we using combinations instead of permutation here?
Right, so in the coin flips, right? So in coin flips, in most cases of coin flips that you probably have seen throughout this lectures as well, is that if I flip 3, let's say like for easy scenario, if I just flip a coin like 3 times, I have 3 tail. They are all equivalent, meaning that the order does not matter. That's why it's a combination, not permutation, right? Because we're looking at exactly how many heads are there, and then how the heads are rotated. They don't matter. Okay. So for example, this is first head, second head, third head, and they're all 3 heads. That the order of the heads show up, you know, whether it's not an issue here. So in another way, that all this is treated as the same configuration. Okay. All right, next question. So you might have seen this question before again. It's a bag of fruits, either bag of fruits, bag of books, and so on. So here you have 8 apple, 4 banana, 7 pineapple, 5 pear. We are going to fill the box with 3 pieces of fruits from the bag. And how many ways are there going to fill the box that have at least 2 types of fruit in the bag? And in this case, I assume that all fruits are distinguishable. Okay, so this is different from the previous question now, is, you know, the orange, assuming all the orange, all the apples are not created equal, that I can see tell the difference between the apples in my bag, right? Maybe one apple has a little bit scar on it, other apple is a little bit eel-shaped, whatever. So I'm assuming all the fruits are distinguishable. Okay. So again, this is this is a counting problem. Okay. And you have 1 minute to try to solve this. And I'm open for anyone who has suggestions how to solve this or how to think about this problem. Okay, a quick hint is that, you know, from the title of the slide is inclusion, exclusion. So you can think about potentially how many different ways to fill the box and exclude the ones that does not satisfy the condition. Right, it says how many ways to fill the box such that there are at least 2 types of fruits in the bag. Alternative solution, which is slightly harder, is to say, well, there's at least 2 types of fruit in the bag or 3 types, right? So that's an alternative solution. But here, actually, what's easier is to try to solve it by using inclusion and exclusion. All right, any volunteer? if there's no volunteer, I'm just going to talk about two parts of this solution. I'm going to use exclusion principle. Anyone?
I can do the first part.
Sure. Yeah.
So I add up all of the numbers. So 8 plus 4 plus 7 plus 5.
That's
is
24.
And then you take a permutation of that. So 24, or I guess.
Okay. So even if I say the fruits are distinguishable, that doesn't mean I need to permute them in the bag. So
Never mind.
It's choosing among 24 pieces. So there's 24 different pieces of fruit. I'm going to choose 3 of them to put in a bag. But when I put in the bag, whether it's ABC versus ACB, they are all in the bag, right? So it's asking how many different ways to fill the bag. So in the bag, it's actually just a counting problem. There's no permutation. So you got the most part of your solution correct, but it's not permutation. In this case, it's counting, okay?
And then in the chat, Brendan subtracted from 24, choose 3, subtracted 8, choose 3, 4, choose 3, 7, choose 3, and 5, choose 3.
Great. So that's exactly my second step. So let's say this number is equal to A. This second number is B. The solution is A minus B. Why? It's because I'm looking at all the ways to fill the box with 3 pieces of fruit. But then I'm going to subtract only the situation where there's only a single type, because those are the things that don't satisfy the condition, right? I count all the possible solutions minus the ones that doesn't satisfy the constraint of the problem. So the second step is basically computing the single type, 3 pieces of the single type.
Is assuming the fruits are distinguishable just a red herring then? Because it doesn't seem like it's affected the problem at all.
No, actually it does matter because specifically, remember, think about each fruit is individual, right? So there's 8 different individual in there. I'm going to choose 3. So yes, they're distinguishable. How would I put it? They are distinguishable when you are choosing from them. If I'm saying they are not distinguishable, the result is actually different. Because I'm going to, like, anytime I choose 3 of them, I'm going to say that, that's just one way that there's if they're not distinguishable, then the counting problem is going to change. It's not going to influence the sort of, it's not going to factor into whether you're going to use a permutation or not in this case, because ultimately I'm asking you to put it in a box, right? But I don't care about how they're arranged in the box. But specifically, if I say, okay, my box actually have different slot that I care about how they're arranged inside the box. For example, if inside the box there is a blue slot, there's a red slot, and then there is a orange slot, then the permutation will matter. Does that make sense? So now I just take A minus B. That's my final solution, okay? And of course, in this particular case, that because of all this, the solution I'm asking for is you can just write this minus the second part, okay? And again, we're going to be very specific in the actual exam to say that, for this problem, I want the integer solution, and for this problem, I just want a justifiable formula. All right? I mean, I just computed because I saw this wasn't too hard, but we'll be very specific for the actual problem. All right, so we're still on counting. We have not moved into probability yet. So this one is how many integer between 1 and 1,000 are relatively prime to 1,000. So there's a definition here. We give a hint of what relatively prime mean. 2 integers are relatively prime if they share no common positive factor except 1. For example, the number 6 and number 15, they are not relatively prime, right? So the hint of this problem, okay, again, I want to first give you 20 seconds to think about how you want to solve this problem. And I'm going to give the hint of this problem. So this is slightly complicated solution, but it's not too different from the previous one where I'm asking how many integers are there that is divisible by 7. Okay, so there's a question or there's a...
Yes. Do we use the exclusion principle?
Exactly. Well, inclusion and exclusion in this particular case. In the previous example, there's 2 scenarios where there's no intersection, but here we need to consider the intersections. So let me give you a hint while you're solving this problem. When I talk about relative prime to a number, first of all, I need to factor out this number to see what are the integer factors are there for 1,000. So what I can do is I say, well, 1,000 is equal to 2 to the power of 3 times 5 to the power of 3. Okay, you can validate this. So this is basically 2 times 2 times 2 times 5 times 5 times 5. That's 1,000. So what does that mean? That means any integer, if they are relatively prime to this, as if they are relatively prime, they should not contain a factor of 2, nor it cannot contain a factor of 5. So we are essentially counting the number of integers that is divisible by 2, divisible by 5. And there's one more sort of tricky part of this question is I also need to count the number of integers that is divisible by 10. All right. So any question or solution?
Yeah, so there is one solution that is 500 plus 200 minus 100. And then I'm not sure if this is a solution or a question, but we've got 1,000 divided by 5 divided by 2 equals 100 with a question mark. Oh, and then there's a solution, 1,000 minus that first term, the 500 plus 200 minus 100, but all of it is in parentheses.
Yes. So the final answer is 400. Okay. So the first answer is correct. So what I want to do is the first number is number of integers that is divisible by 2. So it's 1,000 divided by 2. There's 500. The second number I need to count is a number of integers that is divisible by 5. That is 200. And third one I need to count is the number of integers that is divisible by 10. That's 100. Okay. What we're going to do is n1 plus n2 minus n3 is 500 plus 200. 200 minus 100, this is 600. So all those numbers are the numbers that is not relative prime to 1,000. And now I'm going to exclude that from the total number because I'm asking the ones that is relative prime. So I have 1,000 minus 600, that's 400. Okay. Of course, the solution is typed here, right? So this is typed here. So the key problem of this is counting how many integers that are divisible neither by 2 nor 5. Okay. All right. Any questions?
Yes. Alanta asked, why do we subtract the 100?
Right. So one of those problems is that when we just count the number of integers divisible by 2 and subtract the number of integers divisible by 5, you are over subtracting because for the number that is divisible by 10, you subtract them twice. So in some sense, you need to add them back, right? So that's why we need to count this. So another way to think about it is really, we have 1,000 minus the number of integers divisible by 2 minus the number of integers divisible by 5. And I over subtracted, I need to add the number of integers that is divisible by 10 because I subtract them twice already. I need to add them back at least one copy. So that is 400. But it's easier to think about the exclusion principle is to say, what are the integers that is divisible by 5 or divisible by 2? If that's this solution here. is I need to add, and then when I add 500 and 200, I'm overcounting the ones divisible by 10. So I need to subtract this overcounted number.
Okay, and then there's also a question, how did you know you needed to use 2 and 5? Still confused on the prime part.
Yes, so you need to use 2 and 5 is because of this relative prime condition. So what is the relative prime condition? If they share no common positive factors except for 1. So the first thing we need to do is to factor out 1,000 to see what are the positive factors it have, right? So it has a factor of 2 and a factor of 5. That is our starting point. Okay, so one thing that remember that throughout this whole semester, when we talk about proofs and so on and so forth, we're always using certain properties like integer division. And things are prime, things are relative prime. In here, relative prime meaning that I need to see what are the factors that are part of 1,000 and to start with the solutions. And the factors associated with 1,000 is 2 and 5. That's where my starting point is. Okay. All right, so let's see. So I think we have maybe enough time to go over one last problem. So I'm going to skip this one. I will try to record the rest of it, and maybe some of those extra problems will move it to the discussion session. So combinatorics, okay? So this is combinatorics, but also this is a probability question. Again, it has 3 parts. So you have a shipment of 100 computers, and among them, there's 4 detective ones. And we're going to choose a sample of 6 computers. So the first question is, how many different samples are there? Okay, you have 100 computers, and you're going to choose a sample of 6. So how many choices do we have?
All right, in the chat, we've got 100 choose 6.
Exactly. So the first problem is relatively easy. Now the second question is, among all those samples, how many samples contain all 4 defective computers?
Couple people in the chat said 100 choose 2.
So that's not exactly correct. Do I have an alternative solution?
Yes, there's 2 more answers saying 96 choose 2.
Why choose 2? Oh, yes. Okay, so it's the second solution. So first of all, let's say C4, which is equal to 1. This is among all the 4 defective ones, I'm going to choose them. And among the remaining 96 of them, I just need 2 more to form my sample. So that is this answer. Okay, so why this first solution is incorrect is because the solution has not forced the constraint that we need the 4 defective ones. And after the 4 defective ones are chosen, you only have 96 choices left. So you can't choose those defective ones again. So that's why it's 96 choose 2, not 100 choose 2. Okay, so now what is the probability? The probability is basically, let's say this number is number B, this is number A. The probability is B over A. That is a probability. And it turns out to be a very tiny probability. It's actually, this is a probability. So I'm not going to spell it out, but this is a probability. Now the last question is, how many samples contain 1 or more defective computers? I will give you a hint. This is a problem where we need to think about exclusion again, the exclusion principle, right? So how many samples contain 1 or more defective computers can be the total number of samples minus the ones that don't contain defective computers.
So in the chat, Sam said 100 choose 6, subtract 96 choose 6.
Perfect. That's exactly the answer, right? So the first term is all the possible samples. The second term is the samples that do not contain any defective computer because I'm only choosing among the 96 good ones, okay? So using exclusion principle, the subtraction is my final answer. Okay, so I'm running out of time, but I must say, so we have a lot of extra problems. What I will encourage you to do is to try to solve them on your own before looking at the solutions. And I will try to record a few extra questions later tonight so you can see how I'm solving that problem. But for each questions, most of them we have solutions. The most important one I want to emphasize is this particular one on conditional probability. And I would really encourage you to try to solve this on your own first before looking at the solution. So among all the practice problem we have today, the conditional probability question is actually one of the hardest one. Okay, you're going to see more practice problem for probability on Thursday's discussion sessions as well. Okay, all right, any last questions you might have? All right, if there's no more questions, I think that's conclude our recitation today. And yeah, feel free to go to office hours, post questions over Piazza, and good luck with your next exam, which is next Tuesday. Okay, all right, thank you.